Hello, and welcome to the last unit of Columbia Green Statistics. Alright, so pat yourselves on the back. We're almost done. There's actually only going to be 2 notes videos for this unit, so this is the second to last video. Take a moment, soak it all in. Alright, so what we're looking at is chi-squared distributions. If you've taken AP Bio, you may have seen these before. If you haven't, in all likelihood, they're going to be new. But what the chi-squared distributions allow us to do is, instead of looking at like individual results, we can look at sort of an entire distribution of results. So let's think back to like some of the things that we did with like M&Ms. All right, we could do a specific test on the red M&Ms, or we could do a specific test on the yellow M&Ms, or the green, or the orange, or whatever. The chi-squared distribution is going to let us look at all of the colors at once. So instead of doing lots of different tests, we can do a single test. All right, and there's actually problems with doing like lots of tests on the same data set. So this gives us a better way of kind of handling it, because we're just doing one test for sort of the entire pool there. All right, so let's start actually working through these notes here. So the first one says, is your die fair? If you were to roll a die 60 times, what do you think the expected number of ones would be, twos, etc., etc.? So if it was a fair die, all right, and we were to roll it 60 times, we would expect 10 of each number. All right, which is no surprise there. Now, what we're going to be looking at is how far do things have to deviate from that expectation of 10 of each number before we say that, all right, this is really unusual, something strange is going on here. So it's the same premise of what we've been doing with hypothesis testing for the last couple of units. It's just the mechanics of carrying it out are going to be sort of a little different. And it says sketch the distribution of what you'd expect to see. So if we put the 1s, the 2s, the 3s, the 4s, the 5s, and 6, all right, this would just be a uniform distribution where we'd expect each of those values to have the same exact probability. All right, and that probability would be 0.167, which again is just coming from the fact that they're all equally likely and they all have a 1 out of 6 chance of happening. So again, most of our distributions are curved, but we did start with these uniform distributions where it's just a straight line, and this situation would be a uniform distribution. Each one of those possibilities has the same sort of chances of happening. So it then goes on to say, just like any simulation we've done all year, before we worry about testing the die, we need to see what the distribution of counts looks like for a truly fair die. All right, this is kind of what we've got here. So our null hypothesis is going to be that the assumed proportions are correct. So we're assuming that each of those die faces has a 0.167 chance of happening, which again is just 1 out of 6. And that's sort of our starting point. We're assuming that we're assuming those proportions are correct. All right, we're going to perform an experiment, and then based on the results, we're either going to say, all right, you know, we don't have enough evidence to say that the assumed proportions are wrong, or we have compelling evidence that the assumed proportions are incorrect. You know, maybe it's a weighted die, and it's not in fact 1 out of 6. So to do this, we are going to need to be able to calculate a chi-squared statistic. All right, so this is sort of the equivalent of our z statistic or our t statistic, only we're using it for chi-squared distributions. So let's talk about how it works. First of all, right there is the symbol that you're going to usually see for chi-squared, and it is a statistic used to test whether the observed counts, so what you get in your experiment, match the counts we would expect according to some model. So just thinking about the die we just talked about, all right, if we were to roll it 60 times, we would be expecting 10 of each, because our model is that each of those sides has a 1 in 6 chance of happening. It's equally likely. All right. And the actual calculation is we're going to add up across all categories. And we'll actually run through an example of this in a second. We're going to sum across all categories, and we're going to do the observed minus the expected squared all over the expected. And again, we'll run through an example in a second, but that's how we calculate a chi-squared statistic. Once we have that statistic, we're going to compare it against a chi-squared distribution. And again, we'll see all of that in just a little bit. Okay? All right, let's flip it over to the back here. So this says, let's start with a computer-generated die. So if we were to use this command in the calculator, it would fill in to L1 60 random integers between 1 and 6, which is effectively like rolling a die 60 times. So this, we're just going to use this to kind of show how a chi-squared statistic is calculated. All right, so let's just pretend, I'm just going to write in some numbers here. Let's pretend we ended up with 12 ones, 11 twos, 9 threes, 8 fours, 8 fives, and 12 sixes. All right, so again, I'm just making up those numbers, but we could have done it on the calculator, got numbers, same thing. All right, expected, again, since all are equally likely, we would have just expected to get this. Now, we know that data collection never works out exactly, well, not never, it rarely works out how you exactly expect it. There's some deviations. The question is, are those deviations significant or are they not significant? All right, and the chi-squared statistic is going to help us answer that. All right, so as far as the calculation goes, all right, it would be 12, which was our observed, minus our expected, squared all over our expected. So 12 minus 10 is 2, 2 squared is 4, divided by 10 is 0.4. All right, this one would be 11 minus 10 squared over 10, which is going to give you 0.1. All right, this is going to be 9 minus 10, which is going to give us -1, and we're going to square that. And hopefully you can see now why we're squaring it, so the positives and negatives don't end up canceling each other out. We've seen this sort of thing before with standard deviation. So this is actually going to work out to be the same 0.1. And then we've got an 8 out of 10 here, which again is going to be -2. But when we square that, it's going to be +4 and then 0.4. And then this one's the same exact thing, so I'm just going to put 0.4 there. And then we've already done a 12 out of 10. I'll just write it again. 12 out of 10 squared divided by 10 is going to be 0.4. All right, so that's the process of going through and calculating a chi-squared statistic. For each category, and for us the categories are the sides of the die, all right, you take the observed minus the expected, you square it, you divide by the expected, and then the last step is to take all of these numbers and sum them together. So 0.4, 0.5, 0.6, 1, 1.4, 1.8. All right, so that would be our final chi-squared statistic for this situation. All right, so one thing you should instantly notice, the lowest a chi-squared statistic could ever be is 0. All right, so that would mean that your observes exactly matched your expected, and then they can only go up from there. So there's no such thing as a negative chi-squared statistic because the squaring is getting rid of any possible negative. So 0 would be the absolute minimum, and then it goes up from there. All right. So below here, we would have had everybody in the class do this kind of like we normally do, and then we would have gathered everybody's data and just see what sort of range of chi-squared statistics we would have seen. All right, and it probably would have been something like we would have had a bunch probably right around here. All right, we might have had some that were lower. Again, it's hard to know exactly what we would have seen, but probably something resembling that. Again, we'll take a look at the actual curves in a second to see what they look like, but it wouldn't be crazy to think if we ended up with something like this as a class distribution. Maybe add a few more dots. But this would be sort of the general idea, and maybe we'd have a crazy one that was way out there. But they'd sort of be in this range, and maybe we'd have like one down here too as well. Again, they can't go, 0 would be the absolute lowest, and then they only go up from there. But we might get some sort of result that looks like this. So let's take a look to see what these curves usually look like. All right. So it says, use your graphing calculator to sketch the shape of 3 graphs of the model, changing the degrees of freedom each time. Use the window X is, all right, all that's set up anyways. So here's my calculator. All right. Here's my y equals. You're going to see that I already have in there chi-squared PDF, x, comma 2, comma 5, and comma 14. Those are the different degrees of freedom. All right, so a chi-squared distribution changes based on the degrees of freedom, and we'll talk about how the degrees of freedom are calculated in a little bit. But this right here is going to allow us to graph them. All right, this chi-squared PDF was in the distribution menu. So if you go to second vars, that's where I got this right here. All right, so if we look at the first one, all right, this is 2 degrees of freedom. All right, that's what our curve looks like. All right, so very quickly, we can see that a chi-squared distribution has a very different shape than a normal distribution. So if we sketch this in here, all right, there's our curve kind of. And that makes sense because, again, our chi-squareds can't go negative, all right? Like they have a limit, all right? 0 is the absolute smallest a chi-squared distribution could be. So pretty clearly it's not going to have like the normal bell shaped curve that we've been using for normal distribution. So here's 2 degrees of freedom. Now let's look what happens when the degrees of freedom increase. So I'm going to go back here. I'm going to turn this one off. I'm going to turn this one on. All right, so here's 5 degrees of freedom. All right, so we get a slightly different shape. All right, it is looking more kind of like the traditional curves that we've been seeing, but it's also clearly still not like a symmetric bell curve. All right, so we've got this, and it kind of goes out that way, which again, there is that hard limit. You can't go below 0, but then it can just continue to sort of go up from there. Now, an interesting thing about these curves is that the degrees of freedom is also equal to the mean of the distribution. So the mean of that curve that we just sketched in below is 5. And the mode of this curve, all right, the most likely value, is the degrees of freedom minus 2. All right, so your mode is the degrees of freedom minus 2, or sort of the peak of your distribution. All right. And actually, the rolling die example is going to have 5 degrees of freedom. And again, we'll see why in a second. But that would say that you would expect most of your chi-squared statistics to be around 3 when you're doing something like a die. Okay? And again, these curves are going to substitute in for like the normal distribution. All right? We're going to see where our chi-squared statistic landed, and then we're going to look and say, all right, like how much of that curve is shaded, and we're going to make the same sort of kind of conclusions that we did previously. We're just going to be using a new statistic and a new curve to do that. All right, so let's sketch the last one. All right, so turn this one off, turn this one on. All right. So what we're seeing is that as the degrees of freedom increase, all right, the curve sort of has a less of a peak, and it also moves out to the right. So like as the degrees of freedom increase, you know, having values way down at 0 become more and more difficult. And the reason is the degrees of freedom is actually related to the number of categories you have. So as your categories increase, the odds that every single category is going to be exactly at the expected value becomes less and less likely. So that's why the curve sort of shifts here. So we'll just shape this in and kind of put it that way. All right. So we can see, again, this new distribution that we're using, this new family of curves, because again, it's not one curve, it changes based on your degrees of freedom, has a very different shape than sort of the normal distribution that we've been seeing before. And what do you notice as the degrees of freedom increase? I would say that it's less skewed. All right, so the curves are less skewed. Or you could also say more symmetric. And also larger chi-squared statistics are possible. So we've got more of the area shifting to the right as the degrees of freedom increase. All right, so more area shifts to the right. And remember, the area is the probability of getting certain values, all right? The area under one of these curves is exactly 1, just the way it was for normal distributions. So when we look at the area, we can think of that as the probability that something is going to happen. All right, so we're actually going to be using these curves for 3 different tests. The chi-squared test of goodness of fit, the chi-squared test of homogeneity, and the chi-squared test of independence. Today our focus is going to be just on this one, all right? And the next set of notes we'll look at these 2 right here. All right? So The goodness of fit test is a test of whether the distribution of counts in one categorical variable matches the distribution predicted by the model. All right. And the key here is that the goodness of fit test is for one categorical variable. When we have more than one categorical variable, that's where some of those other tests are going to come in to play. But when we just have a single categorical variable, we're going to be using what's called the goodness of fit test. All right. So let's talk about actually carrying out one of these tests. So the procedure is pretty much exactly the same procedure we've been following. All right, you want to make sure that you've met your conditions, and we'll talk about what those are in a second. You want to state your hypotheses and your alpha or your threshold value. You want to compute your chi-squared statistic. Then we're going to use the distribution to calculate a p-value, and then we're going to write our conclusion. So the steps are exactly the same. The only difference is how we calculate our statistic and the distribution that we're using to evaluate what that statistic means. All right, so conditions that have to be in place. All right, 1, this only works for categorical data. All right, so in the previous units, we started with categorical data, then we did quantitative data, and we kept going back and forth between categorical and quantitative. Categorical would be the proportions, quantitative would be the means that we were calculating. With this one, it's just straight categorical data. We have our usual independence condition, which can get tied in with like the 10% condition. If you don't have true independence, you have to make sure your sample is less than 10% of the population. All right, sample less than 10% of the population. You want to have a random sample, all right, so everything should be done and be randomized. And then the last piece is the expected count should be at least 5 for all categories. All right, so it doesn't matter whether you observe 5 across all the categories, but you should be expecting at least 5 results across all of the categories. As far as the hypotheses go, it's always going to be the same hypothesis. It's either the null is that the assumed proportions are correct, and the alternative is that the assumed proportions are not correct. All right, so that's exactly the same as it was. Well, they're not exactly the same, but those stay the same. Like, no matter what we're doing, if you're doing a goodness of fit test, your null is that the assumed proportions are correct. Your alternative is that the assumed proportions are not correct. And then your alpha is going to just be the 0.05 that we've been using. All right. When we come back, we'll actually go through a full test. We'll calculate the statistic. We'll calculate the p-value. We'll write our conclusion. And then we'll go and do some more examples after that. All right, welcome back. So the actual activity was going to be sort of like dealing out cards. So similar to the idea of like a die, everybody would have been given 6 cards, 1 9, 1 10, 1 jack, 1 queen, 1 king, 1 ace. You would have shuffled them up, and you would have dealt out a card, see when it was, recorded it. Put the card back in, shuffle it up, deal out a card, see what it was, recorded it. We also would have had a little contest where people were trying to guess what card was going to come up. But ultimately, it's kind of the same as rolling a die. It's just instead of rolling a die, we're shuffling up 6 cards. And clearly we can't really do the who got the most guesses right. So again, I'm just going to write in some numbers here. But if there are 6 cards and we're shuffling them up each time, we would expect to get the same number of 9s as we got of 10s, as we got of jacks, of queens, kings, and aces. All right, no one card would have been more likely than another. So again, to keep the math easy on this, let's just pretend we did this 60 times, where we like shuffled up those 6 cards, revealed one. All right, put that card back in, shuffle them up, reveal another one. We would have expected that over 60 times we would have gotten 10 9s, 10 10s, 10 jacks, 10 queens, 10 kings, 10 aces. All right, again, we know that it's not likely that we're going to get exactly that, but we're probably going to be sort of in that range. All right, so let's imagine that we actually did it, and then when we did it, we ended up with 7 9s. We'll do 9 10s, 9 jacks. We'll say that we got the exact right number of queens, but we ended up with more kings, and we ended up with 1 extra ace. All right? So those were our results from our imaginary experiment where we're dealing out cards. And then we'd go through and we'd calculate our chi-squared statistic, just like we did before. So 7 minus 10 squared is going to be -3. Squared is going to be 9, divided by 10 is going to be 0.9. All right, and I'm not going to go through and show the work for all of these because it should be pretty clear at this point how this works. But this would give us 0.1. This one's exactly the same, so it would give us 0.1. All right, this we hit it right on the mark. So that would just be 0. All right. This one's going to be a little bigger, all right, because we were 4 off the mark there. So it's actually going to work out to be 1.6. And then this one was pretty close. This one's pretty much the same as 9 out of 10 because the negatives are going to disappear. So this is just going to be another 0.1. And if we add those all up, we end up with a chi-squared statistic of 2.8. All right, so we can see that if you end up way above 1, it can have a pretty big impact on your chi-squared statistic. Like our chi-squared statistic is 2.8. All right, more than half of that is coming just from the deviation from the kings category. All right, so 1 or 2 that's way off can really drive this number up. And what we're going to see is the larger this number gets, the smaller your p-value gets. All right. So let's actually kind of work through the calculation here so that we can see how this works. All right, so we have our chi-squared statistic. Our next step is to calculate our p-value. So the degrees of freedom is k minus 1, where k is the number of categories. So for us, we had 6 cards, which were our 6 different categories. So we have 5 degrees of freedom. All right. And then on our calculator menu, all right, so if we turn our calculator on, let's get out of here. We go to second vars. We scroll down to chi-squared CDF, not PDF. PDF was just for making the graphs. All right. The lower bound is going to be our chi-squared statistic. So when we just went through that, we ended up with a chi-squared statistic of 2.8. So 2.8 is our lower bound. And then our upper bound is almost always just going to be 9999. So what's nice about these is you don't really have to think about, like, do I go to negative 999 or positive 999? There is no negative 999. Remember, this distribution kind of has that hard stop at 0, and it can't go any lower than 0. And then our degrees of freedom were 5, which again is 1 less than the number of categories. We had 6 categories. So that's right there. All right, plugs it in. I hit enter. All right, so let's just write this here. So chi-squared CDF from 2.8 to 9999 with 5 degrees of freedom gave us a p-value of 0.73, which is basically saying that this distribution that we got, even though it wasn't 10, 10, 10, 10, 10, 10, it wasn't very unusual. All right, it's with 60 trials, it's not that crazy that you're going to end up with one at 14, a couple at 9, one at 7. Like, this is all within the realm of sort of normal. You had a 73% chance of getting a chi-squared statistic of 2.8 or smaller. All right, so our conclusion is pretty much the same as it always has been, because our p-value is over 5%. We fail to reject the null. All right. And the null, remember, was just, the null was that our assumed proportions are correct. So our assumption that you should get 10 of each, or that each should have a 1 in 6 chance of happening, we were not able to reject that assumption. So we're still going with the assumption that each one of those were equally likely, which again, it should have been. All right, there's no reason it wouldn't have been. All right, which is why we're getting such a high p-value there. All right, so let's take a look at an example of these, and then I'm also going to show you how we can use the calculator to do these. Because again, I always show you sort of the long way so that you see what's happening, but most of the time we are just going to be doing these using the tools on our calculator. So a study of, I actually changed it to 700 accidents, involving cell phone use were collected, and the days of the week on which accidents occurred were recorded. Are motor vehicle accidents involving cell phone use equally likely to occur on each of the 7 days of the week? All right, so we're testing, are cell phone accidents equally likely on each day of the week? So if there are 700 accidents in total, and the assumption is that they're equally likely, we would expect to see 100 on each day. All right, that would be if everything was equally likely. However, when we record the data, we don't see that. All right, we see 20 on Sunday, we see 133 on Monday, 126 on Tuesday, 159 on Wednesday, 136 on Thursday, 113 on Friday, 13 on Saturday. All right, so just looking at it as a human being, it looks like there's way less on the weekends and way more during the work week. All right, but you know, our intuitions as humans is not always great. So we're going to run this through sort of the test to see whether or not this is unusual enough that we can say, all right, it's in fact not equally likely. All right, so we run through the same process we normally do. All right, we start with a null, which is that the assumed proportions are correct. And in our case, that's just 1 out of 7 for each day. That would be equally likely. And the alternative is that the assumed proportions are not correct. That's kind of our intuition that there's less accidents on the weekend. All right. And then again, we'd have our alpha of 0.05. Now, as far as doing one of these on the calculator, all right, to run one of these tests, you need to go to Stat, Edit. If you've got things in L1 and L2, you're going to clear them out. All right. L1, we're going to put our observed data. So that's where I would put 20, 133, 126, 159, 136, 113, and 13. All right, there's my observed data. In L2, I'm going to put my expected data. And again, if there were 700 accidents in total, there's 7 days of the week. So we're expecting 100 on each day. All right. So what we can do is we can now go to Stat. Let's get out of here. Stat Tests. All right, same menu we've been going to, and we go down to the chi-squared goodness of fit test. All right, observed we put into L1, expected we put into L2, so we can leave that all alone. And then remember, your degrees of freedom is 1 less than your number of categories. So we had 7 categories, so our degrees of freedom would be 6. All right. So let's make a note of that here. So 7 categories. Don't accidentally count total because total is not a category. So that means we have 6 degrees of freedom. All right. So if we go to calculate here, we will get our chi-squared statistic. All right. So in this case, our chi-squared statistic is very large. It's 206.8. All right. And again, that makes sense because we did 100 minus, let's do this one. 100 minus 20 is 80. 80 squared is like 6,400. You're just going to end up with really, really big numbers there. As you sort of work through all of this. So we're getting a very large chi-squared value. And then notice our p-value is super, super small. All right, so our p-value is 6.77 times 10 to the negative 42nd. All right, that is a really, really, really small value because it's pretty clear that this assumption that accidents are equally likely on all 7 days is not really true. And then what we have here, if you look at that Cntrb, those are the different components of your chi-squared statistic. So if you remember when we were working these out, all right, we had this table here, and these were the individual components of the chi-squared statistic. All right, so we can see that, you know, what is it here? Sunday contributed 64 out of the 206.8. Monday was 10.89, Tuesday was 6.7, Wednesday was 34, Thursday was 12, Friday was 1.69, and then Sunday was 75.69. So you can look at this to sort of determine what's driving your result. So in our case, this large chi-squared statistic was driven by the results on Saturday and Sunday. All right, Saturday and Sunday were so far from what were expected that it made our chi-squared distribution really large, our chi-squared statistic really large, which then gave us a really small p-value. So for this one, we would say, because our p-value is under 5%, we reject the null. All right, and if we were trying to explain what was driving that, this result is being driven by Saturday and Sunday. All right, those are the two where we're getting really large components to our chi-squared statistic. All right, so that kind of shows you how we can do one of these using the calculator. All right, so let's take a look at two more, and then we'll wrap it up. So, what's your sign? The University of Chicago's General Social Survey is the nation's most important social science sample survey. For reasons known only to social scientists, the GSS regularly asks subjects their astrological sign. Are signs equally likely? Which is basically another way of saying, are births spread out equally over the year? All right, because you've got to think there's signs, they each take up a certain part of the calendar. So assuming births are spread out over the year, then astrological signs should be pretty spread out in an equal way. All right. So let's take a look at kind of how we would do this here. So first things first, we have to figure out what the expected values were. Now on the last one, I kind of the numbers were so easy that I was just like, oh, it's clearly going to be, 700. But on this one, it's not quite so clear. So what you want to do for something like this is say to yourself, all right, here's all of my data that's observed, and we're going to sum all of them. All right, so we're going to take all of those numbers and we're going to add them together. All right, so take it on faith that if we added all of those numbers together, it would work out to be 2,776. Now, there are 12 months, or 12 signs. All right. So if we divide that number by the 12 signs of the zodiac, what we would get is, let's see, 2,776 divided by 12. 231.3 repeating. 231.3 repeating. All right, so that would be our expected value for each of those signs. All right, each of those we would be expecting 231.3 repeating. So now that we have that, we can go through and do the rest of this as we just kind of demoed. So we start with our null, h sub 0, the assumed proportions are correct, and then we have an alternative of the assumed proportions are not correct, and then we have an alpha of 0.05. All right. Now, what I'm going to do now is, instead of making you watch me type this in, I'm going to stop this video here. I'm going to type the data into the calculator, and then we'll pick it up when I come back, and then finish the last problem too. Alright, so welcome back. So you can see here, I now have all of my data in L1. Alright, that's the observed data. And then in L2, I have the expected data, which is 231.33. And again, you can either type in the decimal, or what I actually did is I just actually typed in 2776 divided by 12 to get the exact answer there. So either way works, but it's just the same number over and over and over again, because we're saying that they're equally likely, so we'd be expecting the same value from each of them. All right, once we have all of that in there, we go to Stat Tests. We go to the chi-squared goodness of fit test. All right, not the regular test. That's what we're going to do in the next notes. All right, the goodness of fit test. Observed is in L1. Expected is in L2. And remember, your degrees of freedom is one less than the number of categories. So since there are 12 signs, that means we have 11 degrees of freedom. It's always one less than the number of categories. So we'll put the 11 in there. We'll hit calculate. All right. We get a chi-squared statistic of 14.12. So our chi-squared statistic is 14.12. We get a p-value of 0.2264. All right. And again, that value is above 5%, so we would fail to reject the null because our p-value is over 5%. All right, and then again, we can sort of scroll through there and see the different components of our chi-squared statistic. So Aries was 0.17, and those are going to be long decimals, so it's going to be a pain to scroll through all these. But you can just see where the different pieces are coming from, how far each one of them is sort of diverging from what's expected. Now in this case, we're not rejecting the null, but if we had rejected the null, maybe we would have like focused in on this one that was like 3.5 or 1.5. Those are all pretty small, 1.2. Or we would have focused in on this one, which was 4.2, as like, you know, which of these categories is sort of driving the result, you know, if we had rejected or had a lower p-value. Now in this case, again, our p-value is 0.22, so none of them are obviously that large, but you can always scroll through that to just see what the different values are, to see what's sort of driving your result. Alright, so let's look at this last problem. Alright, biologists wish to cross pairs of plants having genetic makeup GG, indicating that each plant has one dominant gene and one recessive gene for color. Each offspring plant will receive one gene for color from each parent. The following table, often called a Punnett square, shows the possible combinations. All right. The table suggests that the expected ratio of green to yellow-green to albino should be 1 to 2 to 1. All right, to test their hypothesis about the distribution of offspring, the biologists made 84 randomly selected pairs of yellow-green parents. Of the 84 offspring, 23 plants were green, 50 were yellow-green, and 11 were albino. Do these data differ significantly from what biologists have predicted? All right, so let's kind of just break this down here, because this problem is different in that it's not saying that everything is equally likely. So if we look at our observed, all right, and we say, let's see, green, what is the other one? Yellow, green, so I'm just going to say YG, and then albino. All right, so we observed 23 green, 50 yellow-green, and 11 albino. Now the expected, all right, we're not just going to take 84 and divide it by 3. All right, we only do that if it says equally likely. All right, we have predictions here. All right, we're saying it should be 1 to 2 to 1. All right, so another way of thinking about 1 to 2 to 1, if we just look at this little chart here, is this should be about 25%, because there's 4 options and there's only one way to get that. This should also be 25%, because there's 4 options and there's only one way to get it. These two should be 50%, because out of the 4 options, there's 2 ways to get that. All right. The other way you might have learned to do this in algebra is just put x's next to each of these and say 1x plus 2x plus 1x equals 100. It would have been 4x equals 100. 100 divided by 4 would have been 25, and that's where you got your 25%, your 50%, and your 25%. So when we're doing the expected, all right, the expected green is 25% times 84, which is actually 21. All right, the expected yellow-green is going to be 50% out of 84, which is actually going to be 42. And the albino is going to be 25% out of the 84, which is going to be 21. All right, so the expected values don't always have to be the same number. All right, if you are given different percentages, that can lead to different expected values. All right, but the rest of it works exactly the same. All right, so our null is that the assumed proportions are correct, and this time, instead of the assumed proportions being that everything are equal, the assumed proportions are that it breaks down 25, 50, 25. The alternative is still that the assumed proportions are not correct. So, in fact, it doesn't break down 25, 50, 25. Something else is involved here. We're going to keep our alpha of 0.05, so that's all the same. And then when we go to our calculator here, all right, we're going to go to Stat, Edit. I can clear out what we did before. All right, L1 has our observed, so that's our 23, our 50, and our 11. And then L2 is our expected. And again, you can either just type in the numbers that we calculated, so like the first one was 21, or you can actually type in the calculation and say 0.5 times 84, 0.25 times 84, and it'll just fill those in for you. All right, but either way, expected doesn't necessarily mean that all of these are going to be the same. They can be different based on whatever the problem gives you. But then once it's in there, you're going to Stat, Tests, you're going to your goodness of fit test, observed, expected. Don't forget to change your degrees of freedom. So again, we have 3 categories, which means we have 2 degrees of freedom. All right? That does not get filled in for you automatically. It's your job to make sure that you go in and adjust that as necessary, because if you don't adjust it, you're going to be using the wrong curve, And if you're using the wrong curve, you're going to end up with the wrong result. Because remember, way back here, we saw that based on the degrees of freedom, the curve has a pretty radically different shape. So if you put in the wrong degrees of freedom, you're going to be calculating the wrong area, which is going to give you the wrong p-value. I mean, if we shade from here to here on this curve, it's a little bit of area. You know, if we shade from here to here on this curve, it's a lot of area. So it's important that you're putting in the right degrees of freedom, because otherwise you're using the wrong curve. All right, so this one would be 2 degrees of freedom. There's our observed, there's our expected. All right, we can hit calculate. We get a chi-squared statistic of 6.48. All right, so that's 6.48. We get a p-value of 0.0392. So in this case, that's under 5%. So we reject the null because our p-value is under 5%. And then again, because we're rejecting it, we might want to say, like, all right, so why are we rejecting it? All right, so if we go through the different components here, all right, we can see that green wasn't that far from what was expected, so that one's fine. Yellow-green was a little further off. We're getting a 1.5 there, but still not enough that we'd suddenly be rejecting the null. And then this last piece here, the albino piece, is where we're getting the largest deviation. All right, that's the largest component of our chi-squared statistic. So that's where the 4.7 is coming from. So this is probably the driver for why we're rejecting. All right, this is the one that deviates the most. And you might be saying to yourself, can I just check the one that's furthest away? You know, a lot of times that's going to work, but do remember that the calculation is observed minus expected squared divided by expected. So it's not just the absolute amount that you're away. Like if you have a really large expected, you have to be further away for that number to be large. If you have a really small expected, you don't have to be as far away for it to be large. So a lot of times, yeah, it's the one that's the furthest away, but not necessarily, just based on how that calculation works. That's why it's useful to look through these and actually check to see which one is kind of driving the result. And we can see, you know, 4.7 out of 6.47 in total. Remember, this 6.47 is just these three numbers added together. And we can see that almost more than 2/3 of it is coming from the albino piece there. So that's kind of the one that's driving our result. All right, so that's how these work. Again, very similar to what we've been doing. But this allows us to look at an entire distribution instead of having to look at just one single category. All right, so instead of just looking at, again, going back to the M&Ms from the very beginning, red M&Ms, we can look at the whole bag as a whole, instead of doing each individual test on each individual color. All right, and there's problems with that because then they're not truly independent because one is related to the other. There's problems because as you perform more tests, the likelihood of errors increases. So for all those reasons and more, this chi-squared statistic and chi-squared distribution gives us a better way of sort of looking at the distribution as a whole. All right, so hopefully this was useful. Let me know if you have any questions, and good luck with the homework and practice.